Hey everybody, in this next video lesson, we're going to talk about something called an acid dissociation constant. We're also going to talk about base dissociation constants. Now, what are these? Well, they're just equilibrium constants, no different than the equilibrium constants that we learned about in a previous unit. But these are specific to acids, and these are often used to measure the strength of an acid. And we talked about the strength of an acid on a previous video lesson. Well, the strength of the acid is depending on how much of it, when dissolved, breaks up into ions. And so this K value, known as a Ka, is an equilibrium constant that is for an acid. So when you are taking a look at how to express that, it's no different than a regular equilibrium constant where you take the products over the reactants and use that to calculate. What this K value tells us is how strong the acid is. The larger the Ka, the stronger the acid. Typically, we don't report Ka values larger than 1 because if it's larger than 1, we just consider it to be strong. But anything less than 1, we have a numeric value. And typically, these numbers get into very small numbers like 10 to the negative third or 10 to the negative fourth. So really, really small numbers. Let's take, for example, this general form of an equation that represents an acid that's weak. And if it's weak, it performs a dynamic equilibrium. It makes hydrogen ions and A- ions. This is the conjugate base of this acid. Well, if we were to write an equilibrium expression, we would put the products on top and the reactants on the bottom and set that equal to the equilibrium constant. So this is just a general expression for any acid. The conjugate base is the A- and the original acid concentration is here on the bottom. This equilibrium expression can be used for any weak acid situation. It's important to note that if you have a polyprotic acid, such as H2SO4, that there's a different Ka value for each hydrogen lost. So Ka1 would be for the first hydrogen lost, and Ka2 would be for the second hydrogen lost. Now we use Ka values for acids, but it works for a base also. We can have a Kb value for a base. So the expression looks very similar to one for a Ka, but we need to have the help of water a little bit in order to show how this works. So the base is B and it reacts with water. And what happens is it strips one of the hydrogens off of water to create OH because we need to have OH in solution in order to be a base. And so the Kb value, once again, is measured by taking the concentration of the products over the concentration of the reactants. But water is a liquid, and so you don't include it in the denominator. And so all you have is Hb, which is the conjugate acid of the original base, times the hydroxide concentration, divided by the original concentration of the base. That's equal to Kb. So this is just when a base is at equilibrium, we have a Kb value for the equilibrium constant. Here's a look at a list of some acids. Some are strong, the ones at the top that you can see have a large Ka value. We don't even express the number here because they're so big, they're often so much larger than 1, we don't even care. But the ones that are smaller than 1, those are definitely listed down here. And as you can see, and I mentioned before, these are numbers that are 10 to the negative third, 10 to the negative fourth. And over here in this right-hand column, they get even smaller yet. And as I mentioned before, the smaller the number, the weaker the acid. I did want to point out here, sulfuric acid has a very large Ka value. That's H2SO4. But if you look just a little bit further down, you can see the HSO4 minus 1. Now this is H2SO4. Once it lost its first proton, they have a Ka value for that. But as I mentioned, a second hydrogen will come off sulfate, and the second hydrogen has a slightly smaller Ka value. Still pretty strong for a weak acid. There's another one over here, carbonic acid. H2CO3 has a Ka value of 4.2 times 10 to the negative 7th. Now that's for the first hydrogen, but for the second hydrogen, which is a little bit further down the list here, you can see hydrogen carbonate is HCO3 minus 1, has a much, much smaller and as a result, much, much weaker acidic hydrogen. And finally, pointing out phosphoric acid, H3PO4. You also have dihydrogen phosphate ion, which is phosphoric acid missing 1 hydrogen. And then you have it down here missing 2 hydrogens. And as you can see, it gets progressively weaker every time you lose a hydrogen. Now finally, we're going to talk about what sort of consequences or what sort of effects do we see when we're talking about strong acids versus weak acids. The stronger the acid, the stronger the electrolyte. What that means is that it will conduct electricity better. And a weaker acid is a weaker electrolyte, so the conductivity is much less. Also, we're talking about how a stronger acid has a lower pH at the same concentration. What that means is if you have a strong acid at 0.1 molar, it's going to have a pH of 0.1. But if you have a weak acid at 0.1 molar, it's not going to dissociate, it's not going to ionize, it's not going to produce the same amount of H plus ions in solution, and pH is measuring the H plus ions in solution. And so because we have less H plus ions in solution, we're going to have a slightly higher pH because of that. So a weaker acid is going to have a higher pH at the same concentration that a strong acid does. Let's go back to that PhET simulation that we looked at the other day, and I'll show this, or hopefully illustrate this. Now, the stronger the acid, the more corrosive it is. The weaker the acid, the less corrosive it is. Also, the stronger the acid, the faster it reacts. Higher concentration of H plus ions means it reacts faster. And this kind of tracks with what we learned about with the kinetics chapter, is that the higher the concentration of the reactants, the stronger the reaction is, or the faster the reaction is. So faster reactions happen with higher concentration of H plus ions, and the stronger the acid, the more H plus ions. Now, keep in mind, all of this is the same for bases, but we're just talking about the acids in all of these. But the same is true for bases. Another thing that you notice is that when a reaction occurs with a strong acid, more energy change happens. So we get more heat released. So usually these happen, there's heat released, and it's more exothermic, so more energy change. Sometimes it might be endothermic, so you get more endothermic energy absorbed, but the stronger the acid, the higher the energy change that occurs when these acids react. That means that the weaker the acid, the lesser the energy change. Strong acids are also better at neutralizing. That doesn't mean they're safer, that just means that there's more heat created when their neutralization occurs. We're going to learn about what neutralization is in an upcoming lesson, but what you need to know is that the stronger the acid, the better it will be at neutralizing. Finally, the stronger they are, the more dangerous they are. Basically, think of stronger acids as more aggressive acids, and so they're more dangerous to handle. If we have strong acids, then we know the concentration of the H+, and then we can calculate the pH from that. But because weak acids don't ionize completely, then it may be difficult to directly find the pH if we know the concentration of the acid, or if we know the pH, we could calculate the concentration of the acid, but it's not quite as straightforward. And so we're going to talk about the calculations involved with weak acids and weak base solutions. The question at the top leads us off. Can we find the concentration of all the parts of a weak acid or weak base situation in solution? And just like strong acids and bases, we can use the pH to find the concentration of our weak acids and bases. We just need to use equilibrium with those pH calculations in order to do this. Now, the first thing we need to do is use the pH to find the H+ concentration in the solution. Whether or not it's strong or weak, the H+ concentration is based on what the pH that we measure is. Once again, considering this general form of a reaction, we can express the Ka as H+ times A- over the HA. Now the pH can help us find the H+, and because we know that this is always happening in a 1-to-1 ratio, then if we know the H+, we also know the concentration of the A-. So as soon as you use the pH to find the H+, you also know the A- concentration. Now, this particular situation only works for monoprotic acids, so any acid with multiple H+ releases would require more complex math, and we are not going to do that in this class. So this is holding true, but not for every situation, but it is true for the situations in our class. Now the only one we don't know would be the HA concentration, and we can use the equilibrium expression along with the Ka value picked out from a table, and the concentrations of the H+ using the pH to calculate this missing variable. So it's just a little bit of algebra solving for the concentration of HA. All right, it's time to put this into practice. I know this seems rather complicated, but we're putting together lots of different parts into one large problem, but you can do it. I trust you. So let me scroll up a little bit to give myself a bit more room underneath so I can write down the problem. So we've got an unknown concentration of hydrofluoric acid in solution, and we know that the pH is 3.25. What is the concentration of the H+ ions and the unionized acid at equilibrium? And so, just like I showed you on the last page, let's first start with a chemical reaction and write out the equilibrium expression. We've got HF giving you H+ and F- because we're working on hydrofluoric acid. Here's the Ka value. Now the Ka expression is H times F- over the HF. Now with the pH, we can take 10 to the negative 3.25 power and figure out the concentration of H+ in the solution. And that H+ will go right here on the top. And that's also the same number that will be for the F- because, as we talked about on the last slide, Since they're 1-to-1 mole ratio, if you know the concentration of the H+, you also know the concentration of the A-. Now we've got the Ka value, so we'll plug that in and stick that in for Ka. So the only thing we're missing here is the denominator, the HF concentration. So with a little bit of algebra, you can rearrange this, and you get a final answer of 4.3 times 10 to the negative fourth molarity. If I rearrange this algebraically, the HF goes up here, and the 7.4 times 10 to the negative fourth goes down here, and I do this times this divided by 7.4 times 10 to the negative fourth, and that's how I got that answer. So now I can answer my two questions. The first question was, what's the concentration of the H+ ions? Well, we calculated that in the process of doing this problem, 5.6 times 10 to the negative fourth. And the amount of non-ionized acid at equilibrium is 4.3 times 10 to the negative fourth molarity.